these are the core requirements that the AP curriculum requires us to understand about what the center of mass, how it can be found. And generally, we're going to be looking at things where the density of the object is consistent. So this might be a typical question that we will want to be able to answer as to where the center of mass is of the system. We can use torque ideas to find the center of mass between two particles. The main idea is that a system naturally balances at its center of mass. So if we locate where that center of mass is, all of the net torque would have to equal zero, or all the individual torques would have to sum up to zero based on whether they are pointed into the page or out of the page. So we'll begin by guessing where we think the center of mass would be. Because there's 2 kilograms on the left and 3 kilograms on the right, I know it's not going to be exactly in the middle. It's going to be pushed a little bit closer to the 3 kilogram object. So I'm just going to take a guess that the center of mass point, the balance point, will be somewhere around here. And you may instinctively know where that is, kind of thinking about ratios, and that's fine. Let's just remind ourselves, though, of how we do a problem like this. The torques must all equal zero, and that's because the angular acceleration of the object is zero, and we can remind ourselves that torque is r times f times the sine of theta. We don't need to worry about this theta angle. We'll think about this as if it were like a beam with masses hanging on to it. So we'll think about it as if it were gravitational forces pulling about this fulcrum. And so the 2 kilogram object would exert a positive torque on the system. And the distance, I don't know. I just know that it's some part of 0.6. So I'm just going to call this distance here x and say that the torque would be x times 20 newtons. And again, times the sine of 90. On the other side, I have the rest of the distance. Again, it's not x and it's not 0.6. It's whatever 0.6 is minus x. So it's the remainder. So that would be a negative torque that's causing the system to rotate in a clockwise direction. So 0.6 minus x. And then the force would be 3 kilograms times 10 newtons per kilogram, so that would be 30. And this has to total up to 0. So we've got 20x minus 0.6 times 30, which is 18. And then I'm minusing negative x times 30, so that's like adding 30x. So I have 50x equals 18. So x comes out to be 0.36. Okay, and that kind of makes sense. That's 0.36. That means the other distance on the other side is 0.24. Okay, so that kind of makes sense. So this is one way of doing it, but let's use this to figure out a formula that will let us handle more than 2 objects in a system. So here we have a general, the 0 point has been defined here at the left-hand side so that everything is positive. I'm going to try to figure out a formula in terms of the variables shown here that would locate where that center of mass point is. I've again made a guess as to where the center of mass is. Doesn't really matter if I've got that right or not. But now I've written all of my distances so that they're with respect to the center of mass point. So again, I'm thinking about those torque ideas. From here, I'll have to do a little bit of work here. So the same sort of an idea that the M1 produces a positive torque, and so I would take this quantity xcm minus x1 times m1 times g, That's my positive torque. And then the other two torques are going to be negative. This time I think I'll just write those on the other side of the equation and say that the torques must balance on the two sides. Remember, that's another way that you can write your work, and it has a few less negative signs. So M2 is at position x2 minus xcm. And then I also have M3 at position x3 minus xcm. Okay, and we can see that our g's cancel out. They don't matter. Let me do a little bit of algebra here. So m1 xcm minus m1 x1 is equal to m2 x2 minus m2 xcm. Again, we're just deriving. You're not going to have to do this on your own. M3 x3 minus M3 xcm. Okay, so I want to notice here that I have a number of terms that have xcm in them. So these three I'm going to bring over to the other side. And so I'd have m1 times xcm, and I would have also, because it would become positive on this side, m2 times xcm. I'm going to add these together and factor, and then m3 times xcm. Right, on the other side, I bring this m1 x2 over the other side. And these are all positive as well. All right, and so we see that the center of mass point, you just have to choose a 0 point and reference everything to it. I end up adding up all of my m times x's, so where the mass is compared to whatever I've considered that 0 point to be, and then I divide by the total mass. And I could have done this for any number of pieces, so let me just say you're just going to add that up for however many pieces you have, and then you're going to divide by the total mass, again, however many pieces you have. So I tend to think about this center of mass formula like this, and again, adding however many masses I need to. On your formula sheet, it's going to look like this, so you want to make sure that you're aware of that if you go look at this later in the year and so forth. Notice that they're using the sigma notation to show a sum of m times x for all the individual pieces on top, and then the bottom here would just be the total of all the masses. So same thing, just a different notation. If the system is in 2 dimensions or 3 dimensions, then we just have the same sort of formula here, but for y coordinates or z coordinates instead. So you would just separate the problem into what's happening vertically, what's happening horizontally, kind of like we've done with other situations like projectile motion and so forth.